everyone. My name is Qinyu Chen, and my topic today is the characterization of shrinkage of 3 alternative eucalyptus species for Chinese eucalyptus plantation. Eucalyptus is an endemic species in Australia, but it has been planted in China for a long time. Back in 1890, eucalyptus was introduced into China for the first time and was used as street trees. Since the 1980s, the Chinese government has advocated a series of forest development programs, such as the Forestry Development Project. The scale of eucalyptus plantation has increased remarkably. The widespread adoption of eucalyptus accelerated in 1990s with the development of clone hybrid technology and the improvement of silviculture. As you can see from this figure, the plantation area of eucalyptus has dramatically increased from that time to the present. However, some problems have also arisen. First, the high demand for nutrition and water resources. In China, the eucalyptus tree has been described as water pumping machine, and the plantation site has been called green desert. And also products of eucalyptus are mainly composed of low-value products like pulp and paper and wood chips. A major problem is collapse, an abnormal shrinkage defect, usually occurring during the drying process, which is a barrier for the eucalyptus wood industry, particularly in the high-end products market like solid wood furniture and flooring. As you can see from these photos here, these lumbers have severe collapse problem, and they are unacceptable in the wood products processing industry. Generally, it is recognized that for the forestry industry, maximizing the total yield or increasing the growth rate of yield has the highest priority. At present, eucalyptus is the most planted species of Chinese plantation and takes up a large number of areas of forest cover. However, there are only a few eucalyptus species are planted, and the most widely planted species in China is the hybrid Eucalyptus euphana x Eucalyptus grandis, for which considerable collapse happens during the drying. So the improvement of the product quality and the willingness to introduce new species are of great importance for the forestry industry, both for sustainable wood production and product diversification. Although eucalyptus is an endemic species in Australia, and samples from many imperial studies were also collected in Australia, wood physical properties also vary among different plantation sites due to different environmental factors. So in my study, physical properties of 3 alternative eucalyptus species that have been planted to a small extent in southern regions of China were examined, including Eucalyptus marginata, Eucalyptus puellaris, and the Eucalyptus obliqua. For each species, the volumetric shrinkage of wooden products is mainly influenced by the wood density. Because of the 6-cell wall, the S2 layer will take a higher proportion in the dense wood and make larger impacts on the wood shrinkage property. And also considering its low microfiber angle, dense wood will produce minimal longitudinal shrinkage while increasing radial and tangential shrinkage. It is anticipated that for most species, there should be a positive relationship between the wood density and wood shrinkage. However, some studies illustrate that eucalyptus wood show markedly different drying behavior. So my second objective is to find the relationship between density and shrinkage. And to keep comparing size stability, I also find the relationship between moisture content and shrinkage. There are 2 states of water in the wood. One is called bond water, which refers to the water that resides in the cell wall. And another one is named free water, which refers to the water existing in the cell lumen. The transition point from a regime that only has bond water to a regime that has both bond water and free water is named the fiber situation point, which is usually recognized around 30% moisture content. As mentioned before, eucalyptus species show a negative relationship between density and shrinkage in some studies, especially when the moisture content is below FSP. The total volumetric shrinkage is composed of normal shrinkage below the FSP, which relates to the fiber cell that is only saturated with bond water in its cell wall, and collapse above FSP, which relates to the fiber cell that has free water in its cavity. And when the density increased, both the thickness and the proportion of fiber cell wall will increase. So it is anticipated that for eucalyptus species, the cell lumen might still hold some amount of free water below FSP, and the decreased degree of collapse caused by free water is higher than the increased degree of normal shrinkage caused by bond water. So to verify this hypothesis, the third objective of my study is to detect the composition of water content below FSP. One tangentially solid board without bulk of each species was prepared for my study. I used a pendulum saw to cut each board along the longitudinal direction into small rectangular pieces. And then I used a pendulum saw to cut them along the longitudinal direction into final samples with a standard size of 8 × 8 × 20 millimeters. The weight of each sample was measured through an electronic balance, and then the dimensions of each sample was measured by a digital caliper. All samples were kept drying in a laboratory oven under 103 degrees for 24 hours. Samples were taken out of the oven every 2 hours, and the weight of each sample was recorded until the absolute value didn't change beyond 5 milligrams, with the final weight measured thus corresponding to the oven dry weight. After that, each sample's three-dimensional sizes were measured again. After measurement, each sample's density, moisture content, volumetric shrinkage, radial shrinkage, tangential shrinkage, longitudinal shrinkage, coefficient of anisotropy, and unit shrinkage was calculated. I also examined the 4 alternative regression models, including linear, exponential, logarithmic, and geometric relationships, to test the relationship between moisture content and volumetric shrinkage, density and volumetric shrinkage, as well as density and unit shrinkage. The comparison of each model's fit was conducted by comparing archaic information criteria. Low-field nuclear magnetic resonance was used to quantify the amount of bond water and free water for additional set of wood samples. Samples was prepared in the same way as in the previous experiment and had the same three-dimensional sizes. I prepared 5 dissecators and added situated solutions of lithium chloride, magnesium chloride, sodium chloride, potassium chloride, and purified water in each lower compartment. Each desiccator was then stored in an environmental chamber at 50 degrees to create 5 humidity levels, which correspond to 5 different moisture content of each wood sample respectively. For each species, 4 samples were put on the plate, on the ceramic plate of the desiccator under each humidity level and kept for 40 days before the NMR test to attain the equivalent moisture content. As we can see from table 1, the density of Eucalyptus marginata and Eucalyptus puellaris are close to each other, while for the density of Eucalyptus obliqua, it is a little lower. The volumetric shrinkage of Eucalyptus obliqua is the highest, more than twice that of Eucalyptus marginata and Eucalyptus puellaris. Similar results are also found in radial shrinkage and tangential shrinkage, which means that this species has a worse size stability and is not suitable to become an alternative species. So when I keep comparing the coefficient of anisotropy between Eucalyptus marginata and Eucalyptus puellaris, we can see that Eucalyptus marginata has the lowest value, which means that this species has the highest consistency between shrinkage along with different directions, which is also of great importance in relation to the drying quality of the wood species. And also you can see from table 2, based on the previous research that illustrates the corresponding relationship between the coefficient of anisotropy and wood quality, it can be told that the corresponding wood quality of the coefficient of anisotropy of Eucalyptus marginata is excellent, while for Eucalyptus puellaris, its coefficient of anisotropy is 1.59, that only corresponds to the normal wood quality. What's more, referring to the hardwood inspection regulations designed by the US National Hardwood Lumber Association, that shows in table 3, for Eucalyptus marginata, both the longitudinal shrinkage and tangential shrinkage meet the requirement of the highest degree FAS, reflecting the excellent physical properties of this species. Through the comparison of AIC values, the linear regression shows the best fitness for the relationship between the moisture content and volumetric shrinkage. As is shown in figure 1 and 2, Eucalyptus marginata and Eucalyptus puellaris have lower slope values, which means that with the moisture content change, both species will have the least volumetric shrinkage degree change. And also the best fit model for the relationship between density and volumetric shrinkage and the relationship between density and unit shrinkage show a similar result that with the density change, Eucalyptus marginata and Eucalyptus puellaris will have low volumetric shrinkage degree change. However, this result is opposite to some previous studies, as well as my hypothesis that there will be a negative relationship between the density and the shrinkage of eucalyptus species. For the result, from the result of NMR test, we can see that there are few amounts of free water. Thus, collapse caused by free water could almost be ignored. While on the contrary, with the increase of moisture content, the increase of the amount of groundwater is noticeable. As a result, the positive relationship between density and shrinkage could attribute to the normal shrinkage caused by groundwater. This study has examined three alternative eucalyptus species as an improvement approach for Chinese eucalyptus plantation industry from low-end to high-end products. Eucalyptus marginata was considered as the best alternative species because of its higher density, smaller shrinkage degree, and lower coefficient of anisotropy compared to those of Eucalyptus euphina x Eucalyptus grandis that has been widely planted in China now. And also based on the best fit regression model of each species, relationships between shrinkage and density are all positive, which is against the result from some previous studies on eucalyptus. Last but not the least, M test verified that the positive relationship between density and the volumetric shrinkage below FSP is mainly composed of the normal shrinkage caused by groundwater. In my study, only one board was prepared for each species, which indicates that the test result may not fully reflect the wood physical properties of the whole tree. Due to different anatomic structures and chemical compositions, wood physical properties also vary within one board. As you can see from these four graphs here, one board that is composed of different parts of the tree may lead to different shrinkage in different directions due to different physical properties between junior wood and mature wood, normal wood and reaction wood, and hardwood and sapwood. And finally, makes the lumbar quality unacceptable. So for future research, more wood samples from different parts of the tree and samplings of a large number of trees should be conducted to get more comprehensive data and a better basis for generalization. In general, people often hold a misunderstanding that as a faster growing species with low density, eucalyptus will not be used in high-end product market. Let alone it also has a serious shrinkage problem, but clarify that even one species with serious shrinkage, if the consistency among each direction is similar, the lumber's quality will be still as good as others. As you can see from this photo, these four timbers all have serious shrinkage problem. But obviously the left two have higher quality because of the higher consistency among each direction. Moreover, considering the environmental influencing factors between each plantation site in China, like the elevation, precipitation, and temperature, which will affect the physical properties of trees, more detailed studies are suggested before large-scale implementation. Although this study shows that for eucalyptus species, there is a positive relationship between density and shrinkage. For the negative relationship between density and volumetric shrinkage, it still needs to be verified that if there are some amounts of free water below FSP that cause collapse. At last, I would like to express my sincere thanks to my supervisor, Dr. Zhan Thomas, for always being patient to give me feedback and putting forward valuable suggestions. I would also like to extend my thanks to my internship host, Dr. Jingbo Shi, for providing me with the opportunity to have this meaningful work and her careful instructions. Additional thanks to my friend Ya Feicheng for his kind support and the assistance with my internship. Okay, thank you.
Hey, Qinyu, could you hear me?
Yeah.
Okay. Thank you for your interesting and meaningful presentation, which gives some alternative species which we can use in the southern area of China. And I'd like to ask you, how do you think the situation in China about most of the area we plant the low quality hybrid eucalyptus in China? How do you think? And do you have any suggestions about the breeding strategy? And secondly, I'd like to ask you, because you mentioned sometimes the normal wood, high density commonly brings to high shrinkage, but it is exceptional for the eucalyptus. So how do you think the mechanisms or the reasons why the eucalyptus with high density but with the low shrinkage? How do you think? And that's it. Okay. And thank you again for your presentation, and thank you for your invitation.
Okay. For the question, for the first question, I think that it can be explained from two perspectives. The first one is that although Eucalyptus euphanax, Eucalyptus grandis has been widely planted in China with worst physical properties, but the plantation area is quite large, and I think the total benefit will be still remarkable. And also from another perspective that although in my study, Eucalyptus marginata shows the best physical properties, it still needs to be conducted more research after mine. So I think that is the answer for the first question. And for the second question, some studies on eucalyptus shows that there is a positive relationship between density and shrinkage, while some others still have the result that there is a negative relationship between density and shrinkage. But for the for most of the results that shows negative relationship, they didn't conduct the NMR test, so we don't know if there are some amounts of free water below FSP that cause collapse.
Okay, so you think the collapse of eucalyptus is a reason for explaining the lower shrinkage for the higher density one? Yes.
Yeah.
Okay. Thank you for your answers.
Okay, the NMR test is used to make to test the amount of bond water and the free water of wood samples, and yeah, and as you can see, this is the test result of the NMR test. The red line means the amount of bond water comes from the NMR test, and the blue line means the amount of free water of the NMR test. And the amount of free water is quite low. So we could almost ignore the collapse caused by free water. Yeah, it's a machine. So you take the samples out of your desiccator. Yeah, we first we put the samples in a test tube, and then I put the test tube into the NMR machine. This one? Sorry, table 2 or table 3? Table 3. This is for all species, not only eucalyptus, but also other species. This is the shrinkage degree for lumber, no matter what species it is. Yeah, no, only hardwood, only hardwood.
Yeah, just a couple quick questions. I think this is working now. I guess the bigger kind of forest conservation perspective on this seems important, and I think the argument for the positives of using these kind of fast-growing species is that and that will produce potentially high quality is that they'll take pressure off of natural forests in China, right? And so I wonder, I mean, this looking at alternative species to bring in that would have acceptable growth rates but much higher wood quality, how do you think that will that potentially actually have a benefit to forest conservation in China?
Yeah, I think the plantation of better of species with better physical properties will not influence the forest conservation in China, because the nature forest, most of them in China is the old growth forest that has unique ecological benefits. But if you look at the plantation site, they may not act as good as the nature forest. So I think the nature forest has a better ecological system, while for the plantation side, it can make more economic benefits.
So most of these eucalyptus plantations are going in on former agricultural land, or the last 25, 30 years, there's been no logging legally anyway in natural forests in China. Where are these new eucalyptus plantations?
Where are these eucalyptus plantations was the question.
Okay, okay, yeah. Yeah. Like, yeah. If you, as I mentioned, only my study shows that this species has better properties. So it doesn't mean that we should plant more eucalyptus or create more plantation site at present. So we can keep what we have right now, and we do not expand more land to plant more eucalyptus in China. So I think it will not bring too much negative impacts to the nature forest.
Okay, well, Thank you very much. Excellent presentation.